Good day to everyone. In this video, we're going to discuss the method of Lagrange multipliers to find solutions to optimization problems. And without any further ado, let us get right into the discussion. So the question before us is to find the largest rectangular box that can be formed if its diagonal is 1 meter long. And I've already drawn a rectangular box with the following dimensions, namely x meters wide, y meters long, and z meters high. And what we want to do basically is to maximize the volume of this rectangular box. So what we're going to do is to form two functions, the first of which is the objective function. So our objective function is, in our particular discussion now, is the volume. So we have to form the volume function v of x, y, z. And in this case, it is given by the product of the dimensions of the rectangle. So x, y, z. So this is, again, the volume of the rectangular box with dimensions x, y, and z. The next thing we have to do is to define the constraint function or the condition function, which comes from the particular condition we are given to us. In this case, namely the diagonal is 1 meter long. So one example of a diagonal of this rectangular box is the segment connecting this corner of the box all the way to this corner of the box on the opposite side. And we are given that this diagonal has measured 1 meter. And now from this one, we have to obtain our constraint function. Now we have to relate the diagonal length to the dimensions of the rectangular box, which from geometry we know is square root of x squared plus y squared plus z squared equal to 1. Now, to facilitate calculations or easier calculations later on, what we will do is to square both sides of this equation so that it becomes x squared plus y squared plus z squared equal to 1. Now take note that any solution that we will obtain for the optimization problem using this as the constraint will actually be the same solution that we will obtain if we use the original constraint. So from here, we now proceed to forming our constraint function. The constraint function can be formed by writing out the following function, g of xyz so we have g of xyz equal to x squared plus y squared plus z squared minus 1. And you might actually ask, can we also form the constraint function 1 minus x squared minus y squared minus z squared? And yes, this is also possible to be defined as our constraint function. And it will also give the same solution to the optimization problem. And so now the next step is to form the function which we call the Lagrangian function. The Lagrangian is the function denoted by capital L of x, y, z, lambda, which is equal to our objective function v of x, y, z minus lambda times the constraint function g of x, y, z and this is equal to, in this case, xyz minus lambda times the constraint function x squared plus y squared plus z squared minus 1. So from here, we try to optimize this Lagrangian function, and we do that by determining its critical points. The critical points can be obtained by first considering the partial derivatives of capital L. So in this case, the first derivative, the one with respect to x, will give us yz minus 2 lambda x. We have L sub y of x, y, z lambda equal to xz minus 2 lambda y. L sub z of x, y, z lambda, which is equal to xy minus 2 lambda z. And finally, L sub lambda of x, y, z lambda is equal to negative of the quantity x squared plus y squared plus z squared minus 1. To obtain the critical points, we obtain each one of these equations to 0. And from the first equation, we get yz is equal to 2 lambda x. From the second, we obtained xz is equal to 2 lambda y. From the third, we get xy equal to 2 lambda z. And finally, from the last equation, we should get x squared plus y squared plus z squared equal to 1. Now, as a check, we can see that the last equation should actually give us back to our original constraint, which is that basically saying that the length of the diagonal for this rectangular box is equal to 1. And so we go ahead and solve for the dimensions x, y, z satisfying these 4 equations. So from the first equation, I will multiply both sides by x so that we will get the following. So we have x, y, z is equal to 2 lambda x squared. I multiplied the second equation, both sides of it with y, so that we will get x, y, z is equal to 2 lambda y squared. And I will multiply both sides of the third equation by z, so that we will get xyz is equal to 2 lambda z squared. Now again, this is lambda. So let me write this out clearly. So this is 2 lambda. And what I will do with these 3 equations is to add up the corresponding sides so that we will get 3xyz is equal to 2 lambda times quantity x squared plus y squared plus z squared, from which we get 3xyz is equal to 2 lambda, because we are making use of this information, which is the constraint condition. And so this gives us a value for xyz equal to 2/3 of lambda. Now take note that we want lambda to be not equal to 0, because we want all of the values of x, y, and z to be positive, and if any one of the values of x, y, z is 0, then no rectangular box will actually be formed. And so what we want is for lambda to be not equal to 0. So continuing, now I will use the first equation again and the equation that we just obtained to be able to find the value of x. So what we can say now is the following. We have x, y, z. So let me change the ink. So x, y, z. If I divide it by y, z, will be equal to 2/3 of lambda divided by 2 lambda x. Now notice again that all of x, y, and z are positive values, and so dividing by yz and 2 lambda x is actually possible. From this, we get x is equal to, the lambda will cancel out, the 2 will cancel out, so this will give us 1 over 3x. And from here, by multiplying both sides by x, we get x squared is equal to 1 over 3. From which we get the value x equal to 1 over square root of 3. And now we can actually argue by symmetry, and we can say that by symmetry, we can also say that y will be equal to 1 over square root of 3, and z is also 1 over square root of 3. So the procedure in obtaining these values for y and z are completely identical with the procedure as to how we actually computed the value for x. So in particular, if we use x, y, z equal to 2/3 lambda, then using the second equation, what we will get is we will have to divide this by xz. So let us make this clear. So xz, so xyz is divided by xz on this side of the equation, and the opposite side is divided by 2 lambda y. So let me, okay, so now the equation will become y will be equal to 1 over 3 lambda, which again will lead us to the value y is equal to 1 over square root of 3. So with this, we now conclude that the dimensions so therefore the dimensions of the biggest box will be x equal to y equal to z equal to 1 over square root of 3 meters. And incidentally, it will have a maximum volume of v equal to 1 over square root of 3 times 1 over square root of 3 times 1 over square root of 3 cubic meters, or 1 over 3 square root of 3 cubic meters. And so this ends our discussion of the method of Lagrange multipliers. Thank you for listening, and I'll see you in the next video.